Hi there! If you work with mathematical models and Python, you may have asked yourself the following questions. Am I using the fastest solver for ODE models as possible? And can I squeeze some extra performance from the solver that I'm using? In this video, I hope to answer these questions in a realistic way. We'll explore how can we modelers working with Python do to numerically simulate our models in an efficient way without wasting time chasing milliseconds here and there. I'll limit myself to ordinary differential equations and discrete stochastic models, also known as continuous time Markov chains, to explore this. And I'm going to run some benchmarks here. So let's cut to the chase. For ODEs, or ordinary differential equations, the most used solver in the Python ecosystem is ODE and. ODE and has been available for a long time and is based on very efficient C and Fortran solvers, which have been optimized over decades to be the fastest possible solvers for these kinds of systems. However, with ODE and, you have to write your model as a Python function. And that causes a problem. Due to the fact that Python is a dynamic language, it imposes an overhead for every function call. This Python function gets called thousands of times, therefore this overhead adds up. So even if you're running very highly optimized C or Fortran code in the background, they still get slowed down. But this is not to say that ODE int is slow. It's actually pretty fast, but not as fast as if you were to write your model in C or Fortran and use directly those libraries in C or Fortran to run your model. But that's not really what we want to do. We use Python in the first place so that we don't waste too much time writing code and actually use our time to simulate stuff, right? So what can we do? Well, actually, the Python ecosystem provides us with very powerful tools for optimizing code. And in this video, we're going to focus on two of them, two of the most popular ones, which are Cython and Numba. Let's start with Cython. Let's take a look at this notebook here. Here we have a simple three-dimensional model known as the Ross-Chaotic oscillator. This is a good example because since it oscillates with wildly varying frequencies, it forces the solver to work hard at it, switching time step sizes back and forth in order to better solve this problem. So this is a good problem for benchmarking. To start with, let's look at the pure Python implementation here that we're going to use with ODE and its newer variant, which is called Solve IVP, which supposedly is a new interface to those same solvers. If we run our model with ODE int, we see that it takes about 136 milliseconds to run 500 time steps with a total of 3,334 intermediate integration steps in the process. Solve IVP, on the other hand, takes more than twice the time, 348 milliseconds, to do the same thing. So what's left to us is try one of our optimization tools. So if we turn our attention to Cython, we can look at the code below and we'll find that the way that we use Cython for optimization is we annotate every variable, everything in our code with type annotation so that those elements in the code can get translated into C and then compiled into native code. That's how Cython works. When we compile our model with Cython, it gives us a very colorful report where it paints in yellow the lines that it couldn't optimize so that we could possibly change the code to help him in its optimization efforts. Unfortunately, as we can see, we cannot optimize the function header itself because it has to be annotated as cpdef, which is a form of annotation in Cython that creates a hybrid object, one that can be called from Python and from C, because that's what ODE int expects. ODE int expects to find a Python function somewhere that it can call. Cython gets some speed up for us. We can get the Cython compiled function run at twice the speed approximately than the pure Python function. That's pretty good, using the same ODE and solver. And now we just plot the solution of this run in a slightly different way, as a phase delayed plot, just for fun. Now let's turn our attention to number. Number is much easier than Python. So does it do as good a job? Well, number does a slightly better job, as we can see. It runs the model a little bit faster, but the advantage of number is that you don't have to do anything. You just annotate your function with number.ngit and you're done. That's pretty good. You have to have in mind that your mileage may vary depending on how simple or how complicated your model is, what kind of calculations it entails. So there's a lot of factors that may affect the benefits you can get from each of those optimization tools. So always test before you choose. And now you know how to perform the benchmarks. It's pretty easy. So now let's move on to the stochastic models. Here I'm going to use my own libraries called epistoch models, epidemiological stochastic models, and let's explore a slightly different avenue for optimization. This library, it is written in the D language. D language is a fantastic compile language which runs at the speed of C and Fortran code, but at the same time is much easier to learn than C or C++ or Fortran. And our implementation, my implementations of those models in D are wrapped for Python, which is not a hard thing to do if you want to write stuff in D and wrap for Python. And so, you know, even if you don't know D, you can call those functions and use those models that are implemented in my library. This library is a new library, so there's not a whole lot of model types in it yet, but it's going to grow over time. So if we look at the first code that we see in this new notebook here, we see first a pure Python implementation of the stochastic SIR model, which takes about 6 seconds to run. If we compare this with the D-wrapped function, it's much slower. I should point out that when we plot the results of this model run with a population of 1 million as it is simulated here, it doesn't seem really stochastic. But that's because the effects of running a stochastic model on a very large population is that the solution, as n grows large, the solution converges to the equivalent ODE solution. That's why stochastic models are mostly more important when you want to explore situations with small numbers where stochasticity may make a difference. Otherwise, just go for the deterministic models. But continuing on, if we look at the performance of the Python wrapped D code, we'll see that it is 6.7 times faster than the pure Python code. But there's still further optimization that we can obtain from this. Since D is a language that's very easy to work with, we can write our parameters and function calls entirely in D and call the library directly without having Python stand in the way. And then we get much faster speeds, actually about 15 times as fast as the pure Python code. Thus, in this video I have introduced you, let's say, 3 ways of optimizing stuff that you may need for your mathematical models. The first one related to ODEs using Python, second one using number, and the third one writing bits and pieces of your code in D and wrapping it for Python or calling it directly. I hope you enjoyed this presentation, and if you like this sort of stuff, give it a like and subscribe to the channel for more content in the future. That's it for now. Bye bye.